I like Sarah's term that she brought up earlier about talking about weird life. And I feel like maybe we should have kept it, maybe we lost something when we convened the topic, because what I'm obsessed with, what Vladimir's obsessed with, and Kobayashi Sensei is obsessed with is weird chemistry. We are so far beyond equilibrium, it's not even funny, right? So what happens when we are really, really far away from conditions that are near and dear and clement to us as organisms? What does the chemistry look like? And I'm basically obsessed with this question, and it's tied to getting really far from equilibrium, about at what point in the prebiotic history did life's organizational attributes arise? I'm not the first one, this is not even my main thing, but I'm obsessed with this question. And there are a couple of ways that we can approach this or think about how it could have happened. One is to just say, well, it showed up, it was an emergent property, and maybe it's nearer to the emergence of a cell than it was to the chemistry. Or perhaps it was, if you strip away everything you know about a cell, everything you know about chemistry and molecules, and you only talk about the relationships among objects, to me it's really intriguing if those organizational attributes go all the way back to the very beginning of the process itself. And in fact, maybe life could have only arisen in those circumstances and localities where the environment is driving organizational attributes to arise among objects from the very beginning. And that's what this talk is about today. So when we talk about making this transition, we have to go from prebiotic chemistry, which is just a bunch of reactions that are occurring and products that are coming out, and coming up with some integrated, holistic entity, something that's reacting with itself and its environment in a very complex way. And when we think about this transition, we can think about it and looking at it from a network perspective. And I know Sarah Walker's been working on things like this for a long time, but something about the network perspective gives us this information when we look at it. So you're looking at a protein interaction map for an E. coli cell. And it might not make a lot of sense to you when you first see it, but to people who study these things, there are a couple of attributes that jump out with a network like this that are very striking. They're very unusual, very unlikely. And one of those things is that the arrangement of objects is very heterogeneous. There's a cluster of very highly connected things in the center, and those are a relatively small number of the total number of things in the network. Around it are a moderate number of moderately well-connected objects, and all around the periphery are a really high number of things that are only connected once or twice. All right? This is what's known as a heavy-tailed distribution. Okay? And we're going to talk about, I'm going to kind of use this as an example to compare these two types of network arrangements and talk about why they're fundamentally different from one another. So if you imagine a network with this, these are two networks with the same number of components, but one of them has an average distribution of connections per object in the network. There's going to be this kind of bell curve. It's called a Poisson distribution. And most nodes have an average number of links. There might be a couple that have one more, two more. There might be a couple that have a little bit less. But basically, it's statistically impossible for highly linked nodes to occur, even with a high number of objects in this system. But this is fundamentally different from a heavy-tailed distribution because there's basically no average. There's no average property that you can extrapolate the kind of network behavior properties based on analyzing each of these individual things. And we see hubs that are really highly connected, but there's relatively few of them. We see a moderate number of things that are moderately well connected, and then a bunch of stuff at the edge that is only connected once or twice. All right? So the kind of analogies I use, this is 20 people waiting in line at the DMV. This is 20 people at a Flaming Lips concert. All right? This is 300 people on a plane from Chicago to Seattle last Sunday. This is AbSciCon, all right? In one of these situations, not a lot's gonna happen. They're random people, they're interacting in very limited ways. Nothing surprising is gonna happen. But when you connect things like this, you get nonlinear behaviors, unexpected things, all right? You can force the system, you can perturb it, maybe nothing happens. Maybe then all of a sudden a step function happens and things change very quickly. And it all comes down to the existence of these links that are concentrated in relatively few objects. So to understand how the system is going to unfold, you really have to understand these really highly linked objects. And when we think about the chemistry, we want to maybe look for systems that look like this from the very beginning. Why do we think this? because we see it repeated as a pattern across all of life's organizational hierarchy, all the way to the top, at the planetary level, the biosphere, in the middle, with groups of ecosystems, populations of cells, and even at the subcellular level with gene transcription rates and protein-protein interaction networks. It's everywhere on this hierarchy. So how far down does it go, and does it proceed all the way back to the origins of life itself? A lot of work has been done kind of describing this. It was a hot topic about 15, 20 years ago. And recent work has been published kind of explaining and describing why this is interesting and what the unique properties of such systems might be as they pertain to prebiotic chemistry. And so I got started on this basically because networks that have been reported recently in the literature, this is kind of where things are progressing. We're not as much interested in whether we find amino acids or whether we find nucleotides or whether they join together. We want to know how they relate to one another and if they interact with one another. Because if they don't interact with one another, you can have all the amino acids you want on all the planets in the solar system. Nothing's going to happen. But the networks we do have are relatively limited. This is almost like a micro network. And you start with, in this case, you're trying to assemble a nucleotide that will lead you into RNA world, and you're trying to assemble it with the fewest steps possible, and you rely on these really reactive, relatively unlikely compounds to be present in high abundance. Things like cyanoacetylene, cyanamide, and your sugar precursors, glyceraldehyde and glycolaldehyde. So my work involved trying to generate these compounds from scratch. You know, don't take them as a given in the environment. Where do they come from? Nitrogen, carbon dioxide, et cetera. And we focused on one of the ways of getting to this step in the shortest way possible would be to use free radical chemistry. Chemistry really far from equilibrium. So what are free radicals? Free radicals are, I don't know, the island of misfit molecules, all right? You start with a nice, stable, clement molecule. It's very happy, relatively unreactive. It's not doing much of anything. But if you plink off one of its electrons in its outer shell, it becomes a free radical. And this radical is very highly reactive and very promiscuous. It doesn't really care what's around it. It's going to react with something eventually, and it's going to do it very, very quickly. So all of a sudden, you've turned your molecules, which are otherwise kind of spectators in the chemistry around it and in the environment around it, things like water or nitrogen or carbon dioxide, all of a sudden, they've become highly reactive and they can interact, the number of interactions that are possible increase dramatically. We haven't added any reactive compounds. We don't need to remove any waste products. We're just adding energy to the system. And we're asking, where does this take us? So we started investigating the radiolytic chemistry of these ribonucleotide precursors, and we found some really interesting things. Over the last 3 years, we've kind of distilled these kind of high-level rules that might point to what a network would look like if we were to build one or actually realize the system. And the first is that you think if you've got energy that's so far from equilibrium that you're going to degrade compounds in equal measure as you produce them. But that's just not the case. In these systems, what you're seeing here is a sequential kind of increase in dose as you go up on this chromatogram. And what you see is that the relative concentrations of some compounds increase with total dose. So you're irradiating the hell out of this system. Some compounds are responding to that in terms of growing over time. And the more you irradiate it, the more compounds are going to come out. They don't get degraded. So that's interesting. It scales with energy input. The next rule we discerned is that we could see repeated actions of the usual suspects, the same radicals showing up over and over and over and over again to kind of impart order on this system. So we didn't get some kind of complicated milieu of sugars reacting with other sugars and spitting out this kind of shotgun blast of compounds. The reason we only see some compounds produced in excess over others is because these same radicals interact with the secondary products, the tertiary products, and end up directing the chemistry in a very specific way. And this was a finding that we just reported over this last year. I think it's really, really profound to think that we can generate our sugar precursors from basically water, hydrogen cyanide, a little bit of energy, and we end up with exactly the sugars that we need for ribonucleotide assembly without creating the excess mixture of sugars that are associated with the foremost reaction. This is a very significant finding, but it allows us to kind of extract this rule, and we saw this repeated in other areas of the work we were doing as well. And the final rule is that it's really interesting to think, but we can do reducing and oxidizing reactions in the exact same volume without a need for spatial or temporal compartmentalization. These reactions can occur micrometers or maybe even nanometers from each other. All right, the species are so energetic and the compounds are moving so quickly in the system that right next to, you can have a water molecule which becomes a hydroxyl radical and a hydrogen radical, or you can have a salt ion that ends up contributing to the formation of hypochlorites in the same system. They don't just back react with each other and dissipate the energy. They end up driving very specific pathways that lead to our nucleotide precursors that we need, our assembly compounds, our condensing agents. When you add up all these three rules together, you can start to ask, okay, what's the smallest box that we could put this in and what would happen? What's the smallest number of reactants that we would need to assemble a nucleotide? What would be the energy source that you'd use as a proxy for analyzing the system? So we came up with this kind of idea that we completely enclose the system, we set it at some average temperature T, and we account for all the schnapps, carbon, hydrogen, nitrogen, sulfur. We throw in some iron sulfide because we know at some point in life iron sulfur clusters are important as metabolic cofactors in enzymes. And we throw in uranium oxide as a proxy for this really high energy system that we're looking for, basically mega electron volts, millions of times past the bond dissociation energy of these compounds. And even just putting them in the box, we can see, okay, there's going to be some network. What is it going to look like? What are the network properties that we observe in this system, and do they look like properties we see in biological systems? And if so, would these network properties confer really unique, dynamic, robust chemical capabilities that we would see in life that we otherwise wouldn't see in these chemical systems? We basically have been collecting free radical and radiolysis experiments that have been reported in the literature over the last 30 years. Some of them are the ones that we helped piece together, you saw in the previous slides. We bend the photonic spectrum into these really coarse categories to account for energy transitions across these thresholds associated with, say, the nuclear force, inner valence electrons, outer valence electrons, and rotational and vibrational modes of the molecules, just to try to keep track of where the non-molecular species in the system and what they're doing, how often they show up. On top of this kind of fundamental base of free radical reactions, we also added redox equations that would naturally occur because you have this abundance of reactive species showing up and getting produced over time. And then we analyzed the network in Gephi to try to visualize what the network looks like. And what does the network look like? It looks like this. It looks something like what we saw in that first slide about the E. coli protein interaction network. We see what we have here are all of the molecular and atomic species in green. We have the equations that connect them in red. And we've scaled the size of the molecular species by the number of times they're referenced in the network. So if you're a hub, if you're connected to a lot of other things, you're being produced in excess, and you're also producing a bunch of other things in excess, you are a big hub in this. And we see one or two major hubs, a small assortment of minor hubs, and then a whole bunch of peripheral stuff that's only connected, say, twice, right, in the system. So let's break this down. Let's put some names on this and see what we're looking at. You can classify these by the types of reactions that are going on. And we have basically all the high energy stuff going on in the lower left-hand portion of this network, stuff that is really, really above the bond dissociation energy. And in between, we have a range of geochemical, chloride, and nitrile reactions that are attenuating this energy, kind of stepping it down from really far from equilibrium and eventually supporting a nest of reactions. It's actually very similar to that micro network that I first showed you that involves the abiotic assembly of a nucleotide compound. And there's a couple of features that are interesting here. One is that there are no parts of the nucleotide assembly equations that are really dependent or contingent upon these high energy stuff. They're kind of secondary and tertiary reactions that have already gone on. So by the time the energy is here, it's really not strong enough to disrupt or disturb the assembly process itself. So let's look at what the inputs and outputs look like. Basically, all of your environmentally abundant molecules that drive the system, undergird the system, are all found kind of at the periphery. And I pick out a couple of the outputs that I think are interesting, namely the assembled nucleotide and gypsum. So gypsum has a very interesting role here in that you're basically sequestering and dumping a bunch of oxygen into an insoluble phase that no longer participates in the free radical reactions. What that means is that if you have a closed box, and you have pyrite and you have apatite, your sulfur and a lot of your oxygen is going to become locked up, and it's going to drive the overall redox state of that system to a more reduced state over time without any external manipulation. So what that means is that it really doesn't matter what the global redox state of the planet was if your box is smaller than a planet and this is a somewhat isolated system from that broader system. Also, what we see here also is that the dominant hubs, the biggest hubs in the system, are all water-derived. The biggest hub is actually the hydrogen radical. Right behind it, water is here, and a hydroxyl radical. So you can kind of see in this radiolytic system that water is not just a solvent. It's not just a remarkable solvent. When you get really far from equilibrium, water is channelizing your energy into very, very specific compounds and very specific chemical outputs of the system. So water, in this sense, is attenuating all of this energy and imparting some level of structure on the resulting network. I think that's pretty remarkable. It's a property of water that we normally wouldn't think about in a chemical context. But there it is. It jumps out plain as day in the network as being all of these major hubs around which everything else occurs. The network connectivity histogram. This has meaning for complex systems theorists, people who know that when we plot out basically the relative occurrence and the connectivity of these different objects, this pattern and the relatively linear slope in log-log space is basically implying that it's possible that at least within the limits of resolution for this very core system, this chemical system might be operating near a phase transition between chaos and order. That doesn't really mean a lot to us that study chemistry, but what it means in terms of systems physics is that it should be a highly dynamic system. It should maintain its overall cohesion even if you introduce disturbances, perturbances, or even if you try to manipulate the external parameters of the system. It should still recapitulate aspects of this broader network framework and structure, which is kind of like what life is, right? We're very versatile. When we reproduce, our child looks kind of like us, but not exactly like us. And we can go to the top of a mountain, we can go swim in a lake. We're still going to be our bodies and still maintain our structure. So there's some aspect of dynamism and robustness hidden in here. But when we dive into why this system might be robust, I just picked out two of these lower level exchanges, which I think we can consider as closed sets of molecules. They're kind of interlinked between HNO, HCO, and CN. And basically these things are occurring very, very quickly at the basal level. If you go a level above that to the compounds that tend to accumulate over time in these radiolytic systems, you see another level above it of more stable, long-lived, but still reactive compounds. And we can, if you look with a close eye, you can discern a broader cycle of each of the compounds needed to assemble a single nucleotide, all occurring at this kind of hierarchical level. Your condensing agents, your nucleobases, your polyphosphates, and your sugar precursors. And at a level even higher than that, your condensing agents and imidazole leaving agents can also be theoretically used to assemble your oligonucleotides at a level that even transcends and explores a phase space above even this kind of radiolytic chemistry. So we think that it might have a lot of these properties that have been described or inferred to have been needed very much at the very beginning for the chemistry of the origins of life to yield a dynamic chemical system like life. And the production of these compounds should be relatively as simple as a rock rolling down a hill in an energetic sense. It's going to happen one way or the other. It's just a question of what happens along the way. And where could this kind of network occur? It really down selects to relatively few places in our universe where you could have both mixed phases of reactants, gas, liquid, and solid, and really high energy radiation coming from either supersolar flares, radiation belts around large magnetic field planets, and radioactive mineral seams in geologic formations with relatively mature crust mantle systems. So there's a lot of questions looking forward about integrating all of these equations and asking whether or not this would be realized in a physical system and whether that system itself would exhibit these kind of emergent properties at a really top level. This is version 1 of the network. Version 2, we're working on getting it out. We'll have a preprint in Chem Archive soon. And I thank you for your time.
As we don't have our final speaker, we do have some time for questions. And before you all head to lunch, because feel free to do so, I've been very encouraged to promote this wonderful new publication from NASA. It's the issue number 7 of the Astrobiology graphic novel series, and it will be given away tonight at 7 o'clock in the poster session, and several of you are pictured here as cartoon characters, so it's a wonderful telling of where life might be found in the universe and the origin of life questions, beautifully, creatively produced by Aaron, who may be here in the room. And with that, let's just also an announcement that after lunch, please return. We're having the next part of the session, session 2, is more complex environments, polymerization, encapsulation, selection. So that's how we're doing this. We're going from the simple formation of the compounds all the way up to complex waveform equilibrium systems. So first question in the center here.
Hi, Mike Wong from University of Washington. This is really fascinating work. So at the plenary this morning, Eric Smith said that in the Origin of Life community, we're very state-focused and we should probably be a little bit more process-focused. So I'm wondering if one of the takeaways from your talk is that we can sort of distill the process behind the network topology of life to essentially the properties of free radical chemistry and that of water. Is that a comprehensive takeaway, or?
Yeah, I think that's an excellent summary. I would specify a couple of things that I think, whether you believe this participated in the origins of life or not, I think there are some really interesting dynamical properties associated with this network that should be investigated. But what I think is an advantage of this particular network in tying to the origin of life, you can create a lot of tractable hypotheses that connect these two. For example, with these closed networks of radicals, as long as the network is closed and as long as at a network level there's some sink for oxygen, it really shouldn't matter what the redox state of, say, the carbon is or the sulfur or the nitrogen. At some point, the system will be driven to be reduced over time. That's an example. Another is that, this is an idea I've been working on recently, is that in making this jump from the radiolytic chemistry to, say, an oligomer chemistry that's explored by the HUD group, Irene Chen, we can actually say, maybe in terms of exploring what functionality means for oligomers, if we're looking for biological functionality, that might be a very limited way of viewing what those short polymers can do. These oligomers might have some emergent functionality with nodes that are located near its emergence within the chemical network that we haven't thought about, either manipulating alternative solvents or turning them into particular substrates that might be useful. So maybe looking at terms of a radiolytic chemical functionality as opposed to a biological functionality for these short oligomer sequences might be productive. Yeah.
Cool, thank you.
Hi, Mike Charlestown, University of Minnesota. Thanks for the really interesting talk. I have, maybe you sort of probably answered it, but I'd like to hear you articulate a little bit better, perhaps. So you describe a really interesting system where you have a high energy source and there's sort of there's sort of consequences of the high energy source. That is very reminiscent of a lifelike system. And I kind of wonder how much of your model is really a metaphor or a model for life?
That's interesting. Okay. I will first state that this is a collection of equations. These represent data. So as much as an ecosystem is a collection of individuals for which we never have complete information, this is definitely data-driven. It's not a model. But I think that's an interesting way of looking at it, especially when it comes to how we think about these things and how we design experiments and we acknowledge the limits and bias that are implicit with any study like this. At what point is it undergirded by a complete mechanistic description, and at what point does it become an inferred model? I don't really have an answer except that there are a lot of other people working on questions like this that have better answers than I do, and I'm sorry I can't give you one, but it's an interesting level of inference when we can actually distill rules that make sense and seem to be repeated. There's something about hierarchy implicit in our ability to make that statement with some assurance.
Thanks. Thank you.
Ralph Budritz, McMaster. Is there the kind of relations in the power law relations that you have for these heavy tails? You showed two of them, this one and the protein one to begin with. Do they have similar indices? Is there kind of universality here in these power laws, or are they quite distinct?
Actually, so there is some degree of universality when we get down to the basic nuts and bolts description for how these things can show up in a physical sense. And I'll defer to Sarah, because I know she studies these things a lot better if you have a follow-up question if I don't answer it sufficiently well. But basically, the exponent is very, very meaningful. I'll also point to Juan Perez Mercader, who's going to give a talk later on. With this kind of exponential relationship between objects, it basically means like the system is not completely frozen and crystallized and rigid, but it also means it's not completely chaotic and doing something different every time you perturb it. So this should give us a number of very interesting qualities at a physical level, such as it might be possible that this is a realization of a chemical computation system, for example. There might be computational primitives that are extractable from certain modes of this system being excited. There's a kind of a class of universality. Whether it transfers to this and what those universal attributes might be, we really have to flesh it out and actually try to build it to make those kind of conclusions.
Thank you.
Vladimir Arpityan, NASA Goddard Space Flight Center. Yeah, I want to comment on the last question on the universality. The point is that this is a nonlinear system that eventually, leads to the self-organized criticality, and the general signature of self-organized criticality is the parallel distribution. And actually, it's interesting that the index of the distribution 0.8 is very characteristic for any kind of system that we observe. Let's say solar flares, they go with the result of the self-organized criticality with the index of 0.8, or earthquakes also go 0.8 earthquakes. So this index is very, very interesting.
Yeah, and I think I don't want to make an overly broad statement, but what we're hoping is that this might be the first organosynthetic system that also has these power law relationship and perhaps self-organized critical attributes.
Hi, my name is Stephen Freed from Johns Hopkins. I really enjoyed your presentation. It was really thought-provoking, and I really appreciated how your discussion emphasized that by photolyzing water with these high-energy photons, you generate H dot, OH dot, and those basically give you ingredients to start to assemble larger things. But I guess what maybe your discussion didn't focus as much on is how if you already have complex molecules and they absorb a gamma photon, there's probably more ways for them to fall apart than for them to come back together. And so I guess my question is, how do you balance, you have this high source of energy, entropy is generally going to favor, complex molecules falling apart. We can draw a network, but that doesn't really tell us much about yield and the efficiency of things kind of staying together versus, kind of falling back apart. So I'm curious what your thoughts might be on that.
Yeah, this is a recurring question about, I think it leads to a broader discussion of plausibility, because at the end of the day, it's not enough to presume that there's an assembled nucleotide on one side of the planet and another one on the other side of the planet from a statistical point of view. They're never going to interact or form a polymer or anything like that. And basically, at that scale, that's like, let's say, this scale, and we're at the scale way down here. What I see here is that you can have a regime within this enclosed box, and you also have a gradient within that box, like if you really want to start to tear it apart. And you can have a really strong zone of radiolysis occurring within a subvolume there that is being attenuated more or less within that volume, and the products are kind of spilling out the edge. So I put up this plot, I didn't talk about it, but basically if you have a really concentrated zone or like a boundary condition where a lot of radiation is spilling in one side, but then there are other parts that have very, very low absorbed dose rates or none. Right. Basically, these products would be expected to spill off the edge of that energy attenuation volume and accumulate in the system elsewhere. Yeah. And so that leads to inferences about how plausible is this system. Would you see it, say, on a planetary scale with supersolar flares impinging on a atmospheric envelope? Would it be raining down below where you're out of reach of those things? Those are all types of environmental inferences that could be made, presuming this kind of heterogeneity within the box itself.
Last question today.
Your network is at a certain energy level. You showed about 6 energy levels from infrared to gamma rays. Mm-hmm. And was that network that you showed for just one of those energy levels, or did you have all of them somehow imposed on one another?
There was no finer binning of the photonic spectrum, and it's really, really coarse, and I admit that it has its limitations, but we were just trying to account for these really gross transformations in entropy production. So the model has no finer division, and I realized that for some species might be very UV sensitive and then completely opaque, invisible, or infrared, or there might be some species that are sensitive within divisions of these bins that really matter. Those are not accounted for in this model. Yeah.
Just a interesting point. I noticed your title slide had vials, glass vials around a cobalt-60 source, and the glass turns brown because the silicate in the glass is being activated by the gamma radiation. So it's a visual indication of some of what you're talking about.
Yeah, very much so. Those are fun experiments to run. And basically, at the end of the day, those experiments are completely hands-off. All of the experiments that we present are more or less hands-off. And that's why we think this might be a self-organizing system. If it has this structure and there's no further internal manipulation, that should be the most likely outcome. Whether it's the actual outcome in a realized system, we would have to kind of more statistically compare and conduct more experiments along those lines. Yeah.
Thank you, Zach, so much for fascinating work, and we'll see you all back here after lunch, and we'll get to even more complex